The course, the Design of Electric Power Systems Part 1 and 2, let's take a look at what we will be getting into. We're going to have an introduction. I want to talk just a little bit about basic safety, because a lot of people get caught up in specs and budgets and schedules and so forth, and you start to lose sight of what happens if something goes wrong. So I'm going to talk a little bit about safety and then codes and standards and economics, then the basic types of power systems, voltage selection, and a lot of this seems fairly simple. Some of it is. Some of it, there are some a lot of details that we will get into. And then we get into load calculations. There were some pretty significant changes to the 2020 National Electrical Code when it comes to load calculations. We'll be looking at that. We'll look then at conductor selection and conduit, overcurrent protection. Then we get into some of the equipment, panel boards, switchboards. And then the last problem, there are a lot of problems in this course. The last problem for Design of Electric Power Systems Part 1 is a lighting design problem. And I've considered taking this problem out of the course over the years. And every time I start asking people, it's like, no, this is the only place where we can actually see how to do this by hand. So you're going to see a basic lighting design problem towards the end of the first module. I also want to talk about what we're going to get into with Design of Electric Power Systems Part 2. And so for Part 2, we're going to move towards equipment. We're going to look at transformers and different types of transformers, K-factor, protection of transformers. And then moving ahead, then we're going to look at motor circuits and sizing and selecting motor protection. We'll look at grounding. We'll touch on a little bit of grounding, equipment grounding in the first part, but the second part we're going to go pretty deep. Talk about the grounding electrode system, high resistance grounding, and a little bit about power quality as well. We'll hit hazardous locations as well, and then a little bit about lightning protection. And then we'll wrap things up talking about generators and automatic transfer switches, interruptible power supplies, just kind of a high-level view, and then a case problem. Now, when I use the term case problem in each module, what I mean by case problem is each course has a series of problems in it. You're going to be solving problems. I'll show you how to solve a particular problem, and then there'll be one for you to solve. And at the end of each module, I have what I refer to as a case problem. It's nothing more than a larger problem where we tie all the concepts together and then turn you loose on it. So when you go through the agenda and you see case problem, it's just kind of the wrap-up problem for that particular module. What I want to introduce in just the design portion of this class is the basics of equipment grounding and the equipment grounding conductor. The concept of equipment grounding is pretty simple. On the right, let's say that this is equipment and this represents the enclosure right here. And coming in up here, this is the phase conductor, as the code calls it, the ungrounded conductor. And then coming out here, this is the neutral conductor, the grounded conductor as the code calls it. The purpose of the equipment grounding conductor is to make a connection from non-current carrying metal back to the source neutral. That's what it's all about. Back to the source neutral. So what that's designed to accomplish is, for example, for this enclosure right here, if this were to be grounded, which it should be, if this were to be grounded, you have the ground conductor coming in and it'll be grounded to the metal. And that ground conductor goes back to the service, and somewhere along the way, it's going to be connected to the equipment grounding bus, which ultimately would be connected back to the service neutral. I'm going to show you some diagrams of this later on. Let me discuss the current limiting fuses a little bit and some of the differences. So I have two fuses right here, and one of these fuses is current limiting and the other is not. And if I were to ask you which one is current limiting and which one is not, looking at it like this, you wouldn't be able to tell. But if I flip them over and I ask which one's current limiting and which one is not, this one is current limiting. And you could tell that because of the notch. And let me explain what the notch is all about. So this fuse, this is a Class H fuse. And a Class H fuse, it has the exact same physical dimension as the Class R, the current limiting fuse. But the difference is the Class H fuse has a much lower interrupting rating. The current limiting fuse tends to have very high interrupting ratings. Let me show you how to select the primary and secondary devices for protecting a transformer. And this is a 225 kVA transformer, and I'm going to walk you through the steps. And this will be using this table and also this table to solve this problem. We're going to size the maximum, not necessarily the optimal, but we're going to come up with the maximum sizes for these devices. So a 225 kVA transformer, everything is a function of load current. Primary load current and secondary load current. So the first place to begin with when you're selecting transformer protection is begin on the secondary. You might think, why the secondary? Why the secondary? Because table 450.3b has the percentages for primary and secondary protection, and the value that you're permitted to use for the primary is contingent on protecting the secondary at no greater than 125%. So we need to evaluate the secondary protection first, and then that will help us determine what we do with the primary. So the secondary full load current, we take the kVA rating, 225 kVA, divided by the square root of 3, and the secondary voltage, which is 0.208 kV. We actually saw this earlier with the short circuit problem. And the secondary full load current is 624.5 amps. Table 450.3b provides us with the appropriate multiplier, and that multiplier is right here. Secondary protection, the secondary device can be sized as large as 125% of the secondary full load current or the next higher device rating. You know, we're looking at Article 310 on ampacities, we're looking at 240 on overcurrent protection, 450 on transformers and transformer protection. And it may seem like the code-making panels for these different articles, they're not talking to each other, but they actually are. That when everything's a function of the load, then it all comes together.